I would like to thank to the organizers of the International Center of Mathematical Sciences for the opportunity given to me to give this course in toric geometry. Now we are starting the first part that will consist of 4 lectures, and in it we will try to develop some dictionary with the needed knowledge from the convex geometry or the combinatorial geometry that will be used all the time in attempt to express algebraic geometric or topological features of this objects, toric varieties, in terms of cones and fans of cones and polytopes in the real vector space, in the real n-dimensional space. So the plan of the first two talks will be we start with the needed information from the combinatorial geometry or convex geometry. We will continue with affine toric varieties today, and this will be the main topics. So they could come from cones, from monomial maps, or from toric ideals. And at the end of this talk, or at the beginning of the next talk, we will pass to abstract toric varieties that will be important, especially in the toric case. So I will pay more attention to the projective toric varieties as well. At the end of this lecture, I will spend 5 minutes for saying something about the motivation of this stuff first, and about references I could give to you in the case that any one of you is interested in reading more about the stuff. In the second part of the mini course, we will cover some topics from different areas of algebraic geometry, of topology, and my intent is to mention something that is kind of application of toric varieties in algebraic statistics, and some stuff that is important for mathematical physics, in particular for mirror symmetry as well. So this will be organized as independent, almost independent lectures that will be based on the stuff we are going to develop now in the next 4 talks. Any questions? At any moment you could interrupt me and ask, make comments, etc., etc. Only I would ask to speak loudly, so I'll be able to hear. So part 1, the combinatorial picture. We have Rn for some n, and we have a lattice in it isomorphic to Zn. This is 3 abelian group over modulo over Z. We will work also with the dual space. I will give, a little bit later, I will give interpretation of these two lattices that will help us to develop a combinatorial picture of the algebra geometric theory that we are going to develop. Two pictures like that. One of them will be covariant and another of them will be contravariant. But just a little bit patience and I will clear what this means. Now we have first definition. We suppose that S is finite set of points with integer coordinates. So first definition, polytope. This is the convex hull of the points in S. This is the set of all linear combinations with non-negative coefficients where A is in S and lambda I is bigger or equal than 0. And one more condition is that we want the sum of lambda I to equal to 1. So this is the polytope standby S. The cone generated by S is sigma equal to all such linear combinations Such a cone will be called rational polyhedral cone, and we suppose that it is strongly convex. So in many of the cases, we will suppose it is strongly convex, which means that it does not contain a whole non-trivial subspace of Rn. Does not contain any one-dimensional subspace of Rn viewed as a vector space. So for briefly, we will denote it as strongly convex rational polyhedral cone. In 99% of the cases we are working with, the cones will be linear. So examples. This cone is convex, but not strongly convex. And this is strongly convex in R2. Right? Both taken in R2. Then we have the notion of a dual cone, which is in the dual space. The dual cone consists of all points in the dual space. The dual cone, it consists of all points U in the dual space, such that the product of UV is non-negative for any V in sigma. For example, so this is first example, second example. I would prefer to give pictures here and there, and to write the text here for some technical reasons. For example, sigma in R2, sigma in R2 gives me sigma dual in the dual plane. Or another example. Sigma in R2 gives me sigma dual in the dual plane. I would like to say also one thing, that not for simplicity but rather for comfort, we will work over C. We could do it over any algebraically closed field, but just for something for concreteness, we will develop the theory over C. So we will speak about complex toric varieties. Essentially, nothing will be changed, at least in this introductory part. Okay, so we have the following Gordon's lemma. Which says that S sigma, which is defined to be the intersection of the dual cone with the dual lattice, this is finitely generated semigroup. So, from now on, we will suppose, if I don't say it explicitly, we will suppose that all cones sigma will be strongly convex rational polyhedral cones, or at least convex rational polyhedral cones. So it is easy to see that if sigma is a rational polyhedral cone, so is its dual. And then we have this lemma. For such a cone, there is always a minimal generating set for this semigroup. And we will see how we use this to define the affine variety, affine toric variety associated with the cone sigma, just in a few minutes. So I need a couple of definitions more. Before that, any questions till now? Everything is pretty elementary. This could be explained to people in the high school, I think, etc., etc. So we need to develop this dictionary just to be able to express essential properties, deep properties, important properties of the objects we are going to introduce in a few minutes. The toric varieties. So, definition by C star, as usual, we mean C without with zero excluded. And with respect to multiplication, this is an abelian group. With T or Tn, I will note the algebraic terms which is n copies of C star for any given n. Another definition. Why this is important? We'll see how this is related to the combinatorial geometry in a few minutes. But it appears that the toric varieties are varieties that contain as an open dense subset a copy of some of this tori in such a way that the action of the torus on itself, it is coordinate-wise action. Each coordinate multiplies each coordinate. This action on the torus itself could be continued to the action of the torus on the whole variety. Any such variety we will call toric variety. In this first part, I will show how we could build arbitrary toric variety from affine pieces. So we first need to introduce and to study a little bit the affine toric varieties, which are subject of this lecture. And then from them, we could glue them together and build arbitrary toric varieties. In the second part of the course, we will show the other approach to this that is based on the geometric invariant theory. And for that, I will need to speak a little bit about the Cox ring. Via Cox ring, it could be done directly. But it is not so intuitively clear as this one. So I'd like to discuss both of them. That is why we need the torus. We will see soon that it is closely related to these lattices I introduced a few minutes ago, and now I'm going to define them, to interpret. I write definition, but it's rather an interpretation of the lattices that are fixed in Rn and in Rn dual. So we have that n is actually isomorphic to the morphisms of algebraic groups of C star into C star to the n, and is called the co-character group, or the group of one of the torus. So here the isomorphism is defined like that. Any n couple in any n couple in n, which we remember that it is z to the n, is associated with the following map. I send each t in C star to the following element in C star to the n. It is t on lambda 1, t on lambda 2, t on lambda n. So this is the co-character group of the lattice, and all the combinatorial picture we will develop in the space with this lattice will have the property to be a covariant description in some sense that will become clearer and clearer, more clear later. I don't want to spend time on it. And here is one notation. When I write an R, this means n tensorially with R over Z, which is, of course, R to the n. So NR means R to the n with n fixed in it. So we have some lattice, we fix the unit vectors, and we make some observations. To continue the definition, we have the group of characters, M, the dual group, and I will show that it is dual, in fact. And it is the group of characters. And it is isomorphic to the group of morphisms of algebraic groups that comes from C star to the n into C star. And each one is defined in the following way. If I have U1 with UN in M, which is of course isomorphic to Z to the n, so these are integers, it goes to the following morphism here. So T1 to Tn, any T1 to Tn in C star to the n goes to the product of Ti on Ui, which is of course in C star. This is, I'm sorry, I'm writing in this a little bit messy way. This is the definition of this isomorphism. And this is the definition of this isomorphism. So, now we start to put some algebra geometric meaning behind the combinatorial picture that we will use all the time extensively. And finally, to say a few more definitions. Even I am not write it as a definition, but as a picture. So I will write tau, a phase of sigma, in the way like this, and I will call tau a facet. Is codimension equals to 1. So this is the main part of the combinatorics we'll need at this level, and later we'll introduce a little bit as as much as it will be necessary. Any questions? Please? Okay. So we continue with the second point, the affine toric varieties, their definition. Let C of S sigma. I will remind that we have lattice and we have a cone which is totally convex rational polyhedral defined by some finite subset of the lattice. The intersection of this cone with the lattice is called a sigma. And this is the polynomial ring, generated by symbols high on U, where mu is in a sigma. This could be interpreted in the following way. I think of this as an n tuple of variables x1 to xn. Each xi has exponent that is ui with integral coordinates. So here I will have 1, 0 corresponding here on 1, 0. This is just x. Here, high on 1, 1. It is xy. And high 1, 2 is equal to xy squared. Then, if I call this and this capital X, capital Y, and capital Z, I see that this cone, suppose that this is in R2 dual, I will see that this cone will define the variety xy minus z squared equals to 0, which is A1 singularity. I like this example very much, and I'll repeat it to analyze it again and again because more features are hidden here. And this is the way we do it with affine toric varieties. We have a strongly convex rational polyhedral cone. We intersect it with the lattice. Then we take the dual picture. Then in this dual picture, the dual cone will intersect the lattice in functions that will be generating the ring of irregular functions. And this ring will define me the affine toric variety. Spec of this ring will be the affine toric variety. So for people who are not in mathematics, I say like that. There was a very big mathematical genius in France in 20th century who figured out that in the case, for example, with algebraic varieties, one space could be uniquely determined by the functions that are called irregular on it. So they form some algebraic structure which is called a ring of functions. You don't need to know the definition of it. You could think, for example, that it is a kind of a polynomial ring of few variables that could satisfy, the polynomials in it could satisfy some relations, as here. Right. This is denoted simply as C of x, y, z modulo xy minus z squared. And this is a ring of three variables, and it defines me a variety that will look like that. I will draw other pictures later because there are more interesting things to say here all the time. Even in June, we will continue with this example. So, once I have the ring, I have the space. And this I will take as a truth, or given truth, as a belief. And this is the way we define the affine toric varieties. And then, from these affine pieces, we could glue abstract toric varieties, and this is the content of the first two lectures I'm going to give. Any questions? Don't hesitate. If anybody wants to ask me something very elementary, there is no problem. So,
this S sigma was the intersection of
S are the integral points here. S sigma are the orange points.
No, that I got from the example, but in your...
Or are they from the dual or the...
For the dual cone.
Yeah.
For the dual cone, we take the intersection of the dual cone with the dual lattice, and then this set will comprise the points in S sigma. So, I could define before that I want to say something that we will use. So we have this is a simple exercise for you. So in many cases I will skip the simple arguments, leaving them as a simple exercise, and in some cases I will skip technically long and boring at this level proofs of theorems, trying to go as far away as possible so that we could reach some areas that are more interesting and more important, and there we will pay more attention to the proofs. But to be correct, I will give good references at the end of this first lecture, so anybody could ask me, of course, but could consult. So we have here, we have the following, that the homomorphisms as C algebra of the ring CS sigma into C, but taken as C algebras are the same set as homomorphisms, and here I will denote it, it is subgroup, semi-group homomorphism, but I will denote it M semi-group to point out that it is multiplicative semi-group. Multiplicative semi-group homomorphisms of S sigma into C. It is very easy. It is very easy to check this. So we have the main definition that the toric variety S sigma, which we define as the spec of this ring. This will be a variety, we'll call it affine toric variety associated with the strongly convex rational polyhedral cone sigma. So which is the cone sigma? I drew it before. This is sigma dual. So sigma this is sigma, and here the point is here the point is 2 minus 1. So this is sigma, and this is sigma dual. The dual cone. So when sigma is small, sigma dual is big, and when sigma is big, sigma dual is small. Further, we have the following lemma. That will distinguish to me which of these points correspond to monomials. So these are like the exponents of monomials, right? Exponents are added to each other and monomials multiply to each other. So what we will have toric varieties defined by ideal generated by binomials. And this is something important. I will say a few words curious about it at the end of the lecture. But before that, I would like to explain which of the points in the lattice M correspond to regular functions on the toric variety X sigma. And we have the following lemma. The following lemma. First, we have that by mu in sigma dual intersected with M. So mu is in M, so it is in sigma dual intersected with M, that is S sigma, if and only if high mu extends to regular function on X sigma. So it is a regular function on the autovectors, and these of them that could extend to the whole variety X sigma are regular functions on X sigma. So these are the functions that will generate the ring of X sigma. And second, we have that mu in N will belong to sigma intersected with N, if and only if the following one parameter group, that is from C star to the torus, which is contained in X sigma, which sends T in mu1, T in mu-n, this is mu1 to mu-n, if and only if this one parameter subgroup extends to a map, again I will denote it along the nu, from C to X sigma, meaning that if lambda mu of 0, which by definition is the limit of lambda mu of t as t goes to 0, you see, originally it is defined as C star. So if we have a limit when t goes to 0, then this is one parameter subgroup of the torus that's embedded in X sigma. Exists. So in this way, given the variety X sigma, we could recover all elements in sigma intersected with n, and then in that way, because sigma is rational polyhedral cone, we could recover the cone sigma itself. So we could go back. I don't want to enter in the details, but this in some sense gives to us an equivalence of categories. And when I associate the combinatorial picture Rn with the variety, the given cone sigma, with all varieties that will appear with such cones, associated with such cones, I will have some kind of a covariant correspondence, covariant functor. And when I associate with the cones the dual picture, then I will have a contravariant picture in the same way as we have in algebra geometry. If I have map of two rings, then the corresponding specs will map in the opposite direction, the same way here. We will see this more and more, but I don't want to go in technicalities. Now, we want to say something about different ways that we could obtain toric varieties. We said about strong comics, rational polynomial cones. Now we will say how they appear from monomial maps. Any questions? Suppose I have a finite set A of elements in M. This is the character lattice of T. So this defines our map phi A of T into C to the S, defined in the following. T goes to any T here, which is n tuple of elements of C star, goes to he on M1 of T, chi on MS of T. So this gives me a monomial map defined by monomials, and then I could take the closure of the image of this map, and this will be affine toric varieties, affine toric variety with affine toric means it has a certain dense subset, a copy of algebraic vectors. So these algebraic vectors will be corresponding to some lattice. And in this case, the lattice is Z times A. So I take all linear combinations of these points here. So example. Let us see how this happens. In fact, we will give two examples that are essentially different. So, example 1. I take A to be equal to the set 2 and 4 in Z. 1, 2, 1, 4. And for Z, then phi A of T. So here we are one variable. The question is the torus is C star itself, and this is equal to T squared T4. So the variety YA is just the hyperbola y equal to x squared. Sorry, the parabola y equals to x squared. So the torus is C star, of course, and the character lattice with character lattice twice z, generated by the even integers, containing the even integers. Right? Here, I would like to show another example for something that will be example that does not enter in our definitions till now. It is example of something that will be toric variety but will not be normal. All varieties are defined. It will appear that they are normal. Later we will see why. But here, what about in the second example? I get A equals to 2, 3. Then I could see that 0, 1 is skipped, then 2, then 3, etc. All of these are here. So this corresponds to T squared and T cubed. So this lattice will define, in this case, let's call it prime. So y corresponding to a prime will be the cusp. Y squared minus x cubed equals to 0 in A2. Right? If I call this x and this y, then I will have this equation. This curve is not normal because it's singular, right? And so we again will have a copy of the torus, a copy of the torus here, because I could map anything without this point is isomorphic to C star here. This is the vertical axis, right? So if I take C star and if I remove the cusp of the curve, the pieces, the open pieces that will remain, they are isomorphic, right? But so there could be defined non-normal toric varieties as well, but in the way we did it before, the toric varieties will be almost normal. And this is one of the reasons that in the beginning, this theory called the objects inside in it, having called torus embeddings rather than torus varieties, toric varieties. So you could embed a torus in a different way, and you obtain different varieties by these different embeddings. Right. So this is something that we may return to it. Later. So, I will give here, I'll repeat here the definition of abstract toric variety. So abstract toric variety, definition, an algebraic variety, X which contains as open, then subset open, then subset such that the action Tn on Tn. What is the action? Any element here is T1 to Tn non-zero complex numbers. And the element here is another such element, say S1 to Sn. So the action is defined by coordinate-wise multiplication. So it is T1 S1, Tn Sn. So this is the definition of this action, such that this action could be continued to action of Tn on the whole X. Any such variety is called abstract toric variety. So we do have this in the case of toric varieties. I will try to show it briefly today. But before that, I would like to show this in more details. So any point, a point T on the torus T, so here I denote the Tn, any point here is a group homomorphism like that, and any point, a point X in X is a semi-group homomorphism, into C, right? And the action, so the action T times X is a semi-group homomorphism that sends U to T of U times X of U. So this is the way it acts using the descriptions we gave before from the combinatorial picture. Let us say a few words about the third way we could define toric varieties, and this is by using toric ideals. Toric ideals are ideals that are generated by binomials. And there is something curious about it, which is based on a lemma which experts say that it is curious but not very plausible. And it says the following. If we have an affine variety defined over whose ring is a C algebra, any such affine variety could be embedded in an ambient space of very big dimension, appropriately big dimension, in such a way that the image then will be defined in this ambient space, will be defined by an ideal which is generated by trinomials. So the binomials, ideals generated by binomials, are in some sense the next step below, or the previous step, I would say. The more general step is the trinomials, right? And it is useful to say a few words about the motivation why we study toric varieties. In the remaining five minutes, I will say a few things about it, and I'll continue with toric ideas next time. Just a few minutes. First, motivation. Toric varieties have very nice structure, very nice geometry that could be expressed in a comprehensive way via convex geometry. And for that, they have been checking stone for many conjectures in mathematics. For example, I worked years ago on what is called the Nash conjecture in R spaces, and although they proved that it is false in general in any dimension bigger than 2, so there are counter examples in dimensions 3, 4, etc., etc. It's a result by Kohler and Tichy that for all dimensions, all toric varieties, it holds. The Nash conjecture does hold. This in a paper of Kohler you can see from 2001. But also there are other reasons that they appear in a natural way in singularities, the relation with Newton polyhedra. They appear in few different areas of topology, like there are generalization of hyperplane arrangements, which are called toric arrangements. There is toric topology, and these are only the few things that I know. There are much more, of course. They are also related with geometric invariant theory, and we will speak about this in June. I will spend some lecture about it, defining the Cox ring. This is another direct way, but much more abstract. And this way is closer to the intuition. So I hesitate a little bit, but decided to start for beginners. I think, from the point of view of pedagogy, this is a little bit better. Although not entering in technical details, but a little bit better for the understanding. Also, there are applications in mirror symmetry and other areas of theoretical physics I'm not competent in. There are applications in algebraic statistics. If you have models, if you have clouds of data of DNA, pieces of DNA macromolecules, then there are toric models there that have very nice properties, very, very interesting, and I will try to spend some time explaining this. This is very, very new subject. I will try to spend some time explaining this. And also, there are much more. For example, many years ago, when I've been in the United States as a PhD student, I've seen an article that showed that toric geometry could be applied in geometric modeling for creating new shapes of cars for the car industry concerns. I don't know much about it, but I know that there are more of it. And during the last years, there is some bloom, second or third or fourth bloom in this area. That's why this was one of the motivations for me to give this mini course. Before finishing, just give me a couple of minutes. I will write down few references that could be useful for you as well. Good job, comments. And we will finish just in time. So, the classical reference, and it still remains like that, is the book of Fulton, Introduction to Toric Varieties. So, for my text, it's good for references, for information, but not so good for beginning course. Nevertheless, it is probably the most cited book in the area. What is very, very impressive is a book of Cox, Little, and Schenk. Toric varieties, very well written. it in 2015. The only problem with it, it's very huge. It's more than 500 pages. But nevertheless, some of the chapters there are really wonderfully written. Cox, he explains in a very good way the stuff, and this could be quite useful. And some of the chapters of it I will use for the second part of the course. Now I used other sources. So we have a very famous article of Cox, David Cox, which says what is a toric variety. It is article from 2003, and also we have Bartel, Kalb, and Fieseler. It is lecture notes, Introduction to Basic Toric Geometry. Too basic. This is also very good. I did use this in this part of the course, Basic Toric Geometry. It's 2005. There are lectures of Ranganathan, very recent, which is toric geometry. Geometry 2020, lecture notes. And another one that I used many years ago, that will comprise, you could obtain everything that probably you may ask questions about the convex geometry, that I'm going a little bit faster over it. And it is called toric varieties and convex geometry, as much as I remember. I read only the second part, which is, first part is convex geometry, and second part it's toric varieties, based on it. It is in graduate texts of mathematics. So I will mention it also. A lot. Graduate text in mathematics, and it's called toric geometry, toric varieties, and convex geometry. But I don't remember the year. About the convex geometry is very well developed here. There, but it gives some time only with convex geometry, and then the rest of the time only with toric varieties, which I think it's a little bit boring. I prefer to mix all the time. But this also could be very useful. There are also many more. But I think for the beginning, this is enough. So this is everything for today. Thank you for your attention. And if you have any questions, I'm waiting. If not, thank you very much again.